dust off your calculator. I'm going to do some calculus. Make sure I'm in radian mode. Alright, looks like we got calculator active on the first one. Looking at those answers. So, I've got f prime here, f of 2 equals this, and f of 5. This looks like a classic fundamental theorem. So from 2 to 5, that's equal to f of 5 minus f of 2, which is 0.4. So f of 5 that I'm looking for is this integral, which I'm going to do with my calculator, plus this. So let's see, I'm going to do math 9. I do the integral from 2 to 5 of the square root 1 plus 2x cubed. Oops, don't need that there. Dx. And I'm just going to go ahead and add my 0.4 right here. 29.005. That's answer choice A. And in 1 sec here. Just going to bring up the answers here to make sure if I do make a mistake, I catch it right away. But I didn't make a mistake there. Next one. Table above shows values of f prime, the derivative of a function f, for selected values of x. If f of negative 0.2 equals 1, what is the approximation for f 0.4 obtained by using Euler's method with a step size of 0.2 starting at x equals negative 0.2? Wow, this is a 3-step Euler's method. That's new. So my x values are going to go from negative 0.2, where I know the y value is 1, and I'm going to step up to, since I'm doing step size of 0.2, step up to 0, and then 0.2, and then 0.4. So to do this, I need to find dy dx, and then I need to do dy dx times my step size, which is 0.2, because that gives me my delta y, right? That's my approximation for delta y, and I should really do that, right? Alright, so at negative 0.2, looks like the slope is 0.8. Multiply that by 0.2, that's 0.16, and then add that to here. That's 1.16. The slope at 0 is 1.2. So I'll multiply that slope by 0.2. Sorry, there's just a beetle crawling on my arm there. And sorry, multiply that by 0.2. That's 0.032. No, it's not. I'm multiplying the wrong thing. Just kidding. Multiply this by. Alright, I've got my calculator. 1.2 times 0.2, 0.24. And then I need to add that here. And that's going to be 1.40. Just check to make sure. Of course it is. And the slope now at 0.2 is 1.7. Multiply that by 0.2, 0.34, and add that here as 1.74. So I didn't need this last value. That was extraneous information. So that's answer choice B. Second derivative of a function f is given by this. How many points of inflection does the graph of f have on the interval from 0 to 3? Definition of an inflection point is where the sign of this changes from negative to positive or positive to negative. So if I graph it on this interval, I just need to look for sign changes. Let's do that. So sine of 3x minus the cosine of x squared squared. Got to be real. Oh, no, sorry, it's just cosine of x squared. Just kidding. That's not there. Sorry about that. And I have an extra set of parentheses, but that doesn't do any harm. If it was a cosine squared, just be careful with calculator entry. That means the whole thing is getting squared, but there isn't one there. And then before I graph, I only care about x values from 0 to 3. So I'm not going to look anywhere else. And I'll look at y values. It doesn't really matter. I just need to see where it crosses. So I'll look from -1 to 1. Doesn't really matter what that is. Oh, and what did I do? Maybe it didn't like those parentheses. Well, let's delete that. I don't really see why that would have caused a problem, but nope. Oh, it's because of that little, I left that thing there. Okay, there we go. 1, 2, 3, 4, 5. 5. All right, just looking for sign changes there. All right. Over the time interval from 0 to 5, and oh, just maybe one last word about that. If I had been looking on the -10 to 10 window there, here, -10 to 10, it might have been hard to see. Yeah, that would be hard to see that crossed there. So I think it's important if you see a graph that looks like this, like that is a bad window for that. So I think we would want to make sure that we have a better look. So 1, 2, 3, 4, 5. And you can always zoom in more on that area if you're not sure. All right. Over the time interval from 0 to 5, a particle moves along the x-axis. And we've got here graph of velocity versus time. Over that time interval, the particle's displacement is 3, and the particle travels a total distance of 13. So the total area is 3. That's this positive, this negative, this positive, and the total distance is 13. And I want to know what's the value of this negative part. Well, let's see if we can figure that out. It's kind of a tricky little question there, isn't it? So if this was the area, if we called this area A, and this B, and this C, let's see if this works. This is my first instinct here. Then I know that if those are all just positive areas, then the total distance traveled is 13. And if I do A, if I recognize that this is negative, if I do minus B plus C, then that gives me a displacement of 3. Right, so adding those two, actually, if I switch the signs of this equation and make this equation -A plus B minus C equals -3, and then I add these two together, I get 2B equals 10. So that area B must be 5. And I actually can't figure out, given this information, what those are, but I can figure out that combined they must be 8, right? So maybe that's 5 and that's 3, who knows what they are, but I know that the value of this integral here from 2 to 4, that's 5. And since this is just a straight up integral and that's underneath, the area is -5. So that's a clever little problem there. I haven't seen one quite like that before. What's the total area between the polar curves, this and this? So between the polar curves. So I think I'm going to go ahead and make a graph of these to see what they look like. So I'm going to go into polar mode to get a picture of this. And let's see what my window looks like here. X min, X max. These have the 5 and the 8 is telling me about how big those R's might be, so I think I'll make, maybe the negative 10 to 10 window wouldn't be terrible here. I'll try that. Negative 10 to 10. And let's go ahead and put these in. So I've got 5 sine of 3 theta and 8 sine of 3 theta. It's a priority flower. And that's this one, right? We did that first. So it's 3 petals. Did I put in the 8 or did I put in another 5 there? Oh, there it is. So it made it twice, that's why. And now it's tracing it over again. And that's actually good to observe that that is the case, because that tells us that the whole graph is being made just from 0 to pi, right? From 0 to 2 pi, it's repeating itself. I'll show you a really quick trick here. If you go to here and change this, the kind of graph that it's making, to do the little like follow the bouncy ball thing. Oops, dang it. There it is. I'm going to graph it again. And so you can see this helps us see, and even if it traces over itself again, it's going to show us that. Alright, so while that's doing that, I have the area between two polar curves here. So that area in general for polar curve is 1/2 r squared d theta. And this one I'm going to have 1/2 r squared d theta of the outside one minus 1/2 r squared d theta of the inside one. And I just need to figure out, I think it's clear, it should be clear that this is the outside one and this is the inside one, right? Is it tracing? So it's tracing it for the second time now. So that's going awfully slow here. So let's think about this. When does this thing double back to 0? So when is sine 3 theta equal to 0 for the first time? Well, that's going to be equal to 0, back to 0, when 3 theta is equal to pi, or when theta is equal to pi over 3. And that makes sense. If it's making the whole thing from 0 to pi, then each one of the 3 leaves or petals of the flower is pi over 3 worth of that 0 to pi. So 0 to pi over 3, this is just one petal. 0 to pi over 3, that's just one petal. And then I need the 3 petals. You could also do, I think if you did 0 to pi, that would work just fine too, and didn't do that 3. That should work fine too. You can check and see if that works. So this is the integral that I need to do. And I'm going to go ahead and knock that thing off. So the only reason I went into polar mode here was to get a look at the graph. Now I'm just going to go back and do the integral on the regular home screen. And it does not matter what mode I'm in to do this. So I'm going to set up that whole thing just like this. So 3 times 1/2, I could factor the 1/2 out to the front, so I have 3 halves times. Here, I need the integral, math 9, from 0 to pi over 3 of this squared. So let's set a parentheses here, then the whole thing 5, this is the outside one, sorry, 8 sine of 3 theta, close that, that's the big set of parentheses, and then that whole thing squared, d theta. And notice on the home screen, since I'm in radian mode, it is giving me thetas. That's nice. If you were using x's here, it doesn't make any difference. Minus math 9, and again I need to go from 0 to pi over 3. Another set of parentheses, 5 sine of 3 theta. Squared d theta, and then close the big set of parentheses at the end. So if we did everything right here, that should be our area there. And we did. So that was a time-consuming problem. But remember, we got more time on these. We got an average of 3 minutes per problem. And how many have I done? Well, that was 76 through 80. So is that the first 5? I think that was the first 5. So I'll go to the next video. And we're doing okay. That was just about 17 minutes. So we got a little bit of time to make up.